what I want to talk about today is something called the Continuum Hypothesis. And this has to do with sets and the size of sets. So we can talk about like two types of sets. So like finite and infinite sets. So if we take like a finite set A, and a set is just like a collection of objects. So yeah, we just look at a finite set A, and we can say it's of size 3 because it has 3 elements inside of it. And we can also construct another set B, and we see that these both have size 3, and they both have the same size even though they're different elements. So it doesn't matter what we put inside of this set, we're just counting the elements inside of it. Okay, but now we want to talk about how can we extend this notion of size, and we're going to construct a new definition called the cardinality of a set. So we say that the cardinality of a set, two sets A and B have the same cardinality if there exists a bijection between them. And all a bijection is, it's a 1-to-1 mapping. So if we can map every element in set A to exactly one element in set B, then there's a bijection between them and they have the same cardinality. So let's, I'm going to keep this up. I guess I'll go over here. So looking back at our sets before, we had 1, 2, 3, and 4, 5, 6, right? If we call this A and this B, 1, 2, 3, 4, 5, 6, we can map everything in set A to set B, like this, or we could have done like that, because it's like a different bijection. There can be like different bijections, but if we can find one between any two sets, and they have the same cardinality. So we say that A and B here have cardinality 3. Okay. So this seems, I'm gonna erase all this. So this definition makes a lot more sense when we look at infinite sets. So for example, if we take our natural numbers, which is 0, 1, and so on, we can't, right, this is infinite, right, so we can't say it has a size like a number. So that's why this definition of cardinality, which is going to make sense in a second. Okay, so let's just take all of our, I'm going to keep going with this, 2, 3, 4, 5, 6, 7, 8, 9, whatever. Okay. So, and we call these are like our counting numbers. This is like another way, natural numbers, counting numbers, right? Now, let's just look at let's only take our odd numbers and so on, right? So let's just call this like O for odd. So we have 1, 5, 6. Okay. It looks like, right, since the natural numbers is both your even and your odd numbers, and your odd number is just odd, it looks like that this set of odd numbers should be exactly half of the natural numbers. Like, so intuitively we think, okay, like the natural numbers is greater than the odd numbers and it's twice as big. But that's actually not true, because if we use our cardinality definition from before, we want to see if we can construct a one-to-one mapping between these two sets. And just kind of like visualizing it here, we can map 1 to 0, or it doesn't matter which way we go, which, because it's a one-to-one, so it doesn't matter which way the arrow is pointing, but we can map from our natural number set 0 to 1, 1 to 3, 2 to 5, 3 to 6, right? We can just go down the line, and we're never going to run out of elements from the natural numbers that we can map to our odd numbers, because they're both infinite. So these are actually the same cardinality. So they're the same size. You can think of it like that. But we have to be careful with our definition of size here, because size and cardinality are a little bit different. Okay, so we see that the odd numbers and the natural numbers have the same cardinality. The same thing, the same argument can be done with the even numbers. So like 0, 2, 4, and so on. And we can also create a bijection with our integers and our rational numbers as well, where the rational numbers are just, I actually don't need to be super formal. The rational numbers are just the set of all ratios of our integers. So we see that the natural numbers, the integers, and natural numbers, the integers, and the our rational numbers all have the same cardinality. And we say that these are countably infinite. And obviously before, right, when we were dealing with finite sets, we just give, like, before we had like 1, 2, 3, 4, 5, 6, we said they both had cardinality 3. Obviously we can't really give like a number as a cardinality here, because there is no number, they're infinite. So we just give it a variable instead. So if something is countably infinite, then we say its cardinality is LF0. This is like, I think this is like Hebrew, a Hebrew letter. Like LF, I think is the A in Hebrew. So LF0 is the cardinality of all of these sets. And this is how we talk about like the size of a set. We just put the absolute value bars around it. Okay, so now the big question here, or I guess if you want to like, it's big. You'll see in a second. Is what about the real numbers? Are the real numbers countably infinite? And the answer is no. And here's why. Okay, I'm gonna erase all this. So the proof that I'm about to show, it's called Cantor's diagonalization argument. And I think his name was like, it's like Georg or George. I don't really know how to pronounce it. But he showed this, and it was kind of like a big deal in the math community, I guess, because at that time, all the mathematicians had thought like, oh, all infinite sets are the same size, like infinity is just infinity. But Cantor showed that there are different sizes of infinity with this argument. So this is like if you want to look this up on your own, diagonalization argument. Okay. So I'm just gonna show this for 4 numbers, right? So the idea is we construct like a table. And on the left side of the table, we're gonna start writing out our natural numbers. And on the right side of the table, we're gonna put we're going to try to put all of our real numbers, right? So let's just start like 0, 1, 2, 3, 4. I'm going to stop here. Okay. And now I'm just going to start writing out like random real numbers over here. So this is like 2, 4, 5, 6. And then, okay. So what this diagonalization argument says is that we're going to shift all of these numbers up by 1, right? So let's just say, right, we're going to shift all these up by 1. So we're going to construct a new number. So it's going to be, right, 4.9966. Okay, so because we've changed the first number in the first, so 0 is our first number, the first number in the first position, the second number in the second position, the third number in the third position, the fourth number in the fourth position, and so on and so forth, we're guaranteed to have constructed a new number because we've changed this diagonal. So if we think about it, if we extended this like obviously we can't capture all the real numbers, but like we can kind of try to visualize it. We're changing the first number in the first position, second number in the second position, third number in the third position, so on and so forth. And then we're guaranteed to generate a new real number because we're changing across this diagonal here. And we're shifting in these places. And so even if we can list all the natural numbers, we're guaranteed to be able to generate a new real number. And so we say that the real numbers are greater, the cardinality of the real numbers is greater than the cardinality of the rational number, or of the natural numbers. And then we give the cardinality of the real numbers like LF1. Okay. So this is like, now we're ready to think about what this continuum hypothesis is saying. So we have this. So we have the cardinality of the natural numbers is LF0, the cardinality of the real numbers is LF1. And we know that this is true, that LF0 is less than LF1. Right? Now the question is, the continuum hypothesis is asking, is there another cardinal number between these two? Right? So do the cardinal numbers look like this? Is it LF0, LF1? Or is it LF0 and then some other cardinal number, LF like 0.5, LF1? Or something like this, LF0, LF.4, LF.5, and then LF1. Right? And it's continuum because, like, do we jump right away? or right, this is like it's not a continuum. It's just you're going straight there, or is there like, are we going to take a continuous path to LF1? So this is what it's asking. And the reason this is a hypothesis is because we don't know, and it's been proven that we can't know. So if we look at the like the set theory axioms, like it's called like ZFC, like I think it's like Zermelo, Franco, and then the axiom of choice, which is just like an axiom of set theory. This shows, like it's been proven that um that these axioms can neither prove nor disprove uh this. So the active research like that's going on today to kind of figure this out is, can we extend our axioms down here to either prove this one way or the other, or the active research is, can we extend these axioms to come up with a resolute answer to this question of, is it just LF0, LF1, or are there cardinalities in between? And yeah, it's kind of interesting that we just look at our axioms here and we don't know the answer. So like it's like, we're thinking math history, like, oh, like we're working like way up here with all the results of our axioms, but this is like axiomatic research, so it's kind of interesting. Yeah, that is the